Today we're going to look at the inverse of an exponential function, which is another function called a logarithm. So as a quick reminder, looking at something in exponential form, we have a base b being raised to a power y, and that is equal to something, we'll say x. When we rearrange in logarithmic form, our base b now goes down as that little b after the log. Our exponent is what the log is equal to. So if we say log bx, we're saying we take b and raise it to some power to equal x. That some power is the y we're looking at. Take a moment to read over the formal definition and kind of get that to make sense. Let's take a look at an example of how we would use this to change from exponential to logarithmic form. Looking at our first example, we have 3 to the power of 3 is equal to 27. 3 is our base. So when I write this as a log, I'm going to write log base 3. And we're saying 3 to some power will be 27. And that power is 3. We read this as log base 327 is equal to 3. We'll do something similar for the next one. So again, we'll start with log. This time our base is 10. 10 to some power is equal to 10,000, so we write it as log 10, 10,000, and that's equal to 4. So you'll see really the log is just equal to that exponent on the base. Now, when we use base 10, we don't always write the base, so we would usually write this as log 10,000. If you see a log and it does not have a base, the base that's implied to be there is a 10. Okay, we can also evaluate logs. Now for questions like this, you need to be able to show how to determine the numerical value without a calculator. So you need to actually show the steps of why is it equal to that, not just enter it in a calculator. So I'm just going to temporarily set this equal to something. So we'll say that log 1000 is equal to y, so we can find out what log 1000 is equal to. Remember, we have a default base of base 10. So we have a base of 10, an exponent of y, and it's equal to 1000. So we're asking ourselves 10 to what power is equal to 1000. Remember, we can write that 1000 as 10 to the power of 3, which tells us that y is equal to 3. So we can see that log 1000 is equal to 3. Okay, try something similar on the next one. All right, let's rewrite this with a y. Y equals log base 1/3 27. Now this one's a little weird because normally with logs we don't actually have a base that is a fraction. If we go back up to our definition of a log, we can have any log that's greater than 0 and not equal to 1, so it actually is allowed. It's just not as common. Now, as an exponent, that would be a base of 1/3 to the power of y is equal to 27. And I would just rewrite these both to have the same base, or a base of 3. 3 to the power of negative y is equal to 3 cubed. So that tells us that negative y is equal to 3, or y is equal to negative 3. Okay, next one. So for the next one, we have log base 6x is equal to 3. We're going to try and find x. So again, we'll rewrite 6 to the power of 3 is equal to x. And we can evaluate that. X is equal to 216. And we can do something similar and have a little more inside the log. So notice this bracket. That tells us that entire thing is part of the log. So rewriting this, we would have 7 to the power of 3 is equal to x plus 2. And we would just rearrange to solve for x. So 343 is equal to x plus 2, or x is equal to 341. Okay. Lastly, a little bit of an interesting one. We have log base 17, 17 to the power of 381. Now we have some really big numbers here, but we can follow similar steps. So I'm going to start off by setting this equal to y. And I'm going to rewrite it. And keep in mind, this entire thing, 17 to the power of 381, all of that is part of the log. So we have 17 as a base to the power of y is equal to 17 to the power of 381. And actually just rewriting it like that did exactly what we needed it to do. We have 17 as a base on both sides, and we can see that y is equal to 381. So that tells us that this entire logarithm is equal to 381. Keep an eye out for that pattern of having that 17 and that 17 to some power, or similarly with other numbers. All right, on to the next page, and looking at the domain of a logarithmic function. So because logs are an inverse of an exponential function, the domain of a log is the range of an exponential function. So that gives us this restriction of x being greater than 0. Also keep in mind, because we have some restrictions on the base of the log, so if you look at an example log like that, it must be greater than 0 and it must not be equal to 1. So keeping those in mind, let's look at identifying some restrictions. Looking at the log on the left, we'll look at this x minus 2. That must be greater than 0. So we'll say x minus 2 is greater than 0, or x is greater than 2. Notice for this case, our base was just a little 3. So there's nothing we need to worry about there, no restrictions. However, when our base is a variable like x plus 2, we'll need to look at that for restrictions, because that's where these restrictions come into play. So we'll be writing out several different restrictions for this. One restriction is that x plus 2 must be greater than 0. And I'll just rewrite that as x must be greater than negative 2. A second restriction is that x plus 2 cannot equal 1. So both of those restrictions are coming from this restriction on the base of a logarithmic function. And that tells us that x cannot be equal to negative 1. However, I also have a third restriction from this x minus 1. That must be greater than 0. So x minus 1 must be greater than 0, or x must be greater than 1. Now, when we have all these different restrictions, we need to look and see, do any of these restrictions encompass another restriction? For example, if a number is greater than 1, we already know it won't be equal to negative 1. So this restriction is taken care of by saying x is greater than 1. Similarly, if x is greater than 1, then we know that x is greater than negative 2 because it's greater than 1. So this one restriction covers all restrictions. This may not always be the case. Sometimes you may have multiple restrictions. But if you do have one that includes the other, then you would just use that for your final restriction. X is greater than 1. Finally, finding the inverse. So we say that the log function is the inverse of an exponential function. The reverse is also true. If you find the inverse of a log, it is an exponential function. If you find the inverse of an exponential function, it is a log. And we're going to follow the same inverse steps we've been following before. So we'll take our equation, we will reverse x and y, we will isolate the power or the logarithm, and we'll try and switch it to the other form. So if we started with exponential, we'll rewrite it as log. If we started with log, we'll rewrite as exponential. And the reason we do that is we will then solve for the new y, which used to be x. Let's look at an example of this. So if I take this first function, this is an exponential function. I'm going to write it as y equals, just to make that a little clearer, 6 to the power of 3x plus 2 minus 4. Now to find the inverse, I'm going to do the inverse in another color. I'm going to switch x and y. So x equals 6 to the power of 3y plus 2 minus 4. Now when we write the inverse, we need to isolate y and write it as y equals. Right now that y is in the exponent. That's why I need to change it to a logarithm. So let's start off by isolating that term. So I'll add 4 to both sides. X plus 4 is equal to 6 to the power of 3y plus 2. Now, there's no way for me to isolate y until I rewrite this as a logarithm. So I'm going to write it as a logarithm, log base 6 x plus 4 is equal to the exponent, and the exponent is 3y plus 2. Changing that form allows us to isolate y. So now I can make it 3y equals log base 6 x plus 4. I'm going to wrap that in a bracket. I should have done that up here too. Minus 2. And y equals that whole thing over 3. Log base 6 x plus 4 minus 2 all over 3. All right, let's try something similar, but going in the opposite direction. So this time we're going to start with a log function. And when we find the inverse, we're going to replace x and y. So we have x minus 3 equals log base 6 2x minus 5. And actually in this case, our log is already by itself. So, oops, that should be a y, since we're switching them for inverse. So x minus 3 equals log base 6 2y minus 5. Now we want to isolate y. Right now y is trapped in the log. So we need to find a way of rewriting this. We're going to rewrite it in exponential form. So in exponential form, we have 6 to the power of our exponent is x minus 3, and that's equal to 2y minus 5. Okay, now it's a little bit easier to isolate y, so we can say 6 to the power of x minus 3 plus 5 equals 2y. And solving for y, we can say y is equal to 6 to the power of x minus 3 plus 5 all over 2. All right, and that's all.